Hello, everyone, and welcome to the Rust in Action book club. Today, we're going to be covering the Prometheus client that we use in GitLab and how it's using Rust. Uh, yeah, so today we have Will, who did the rewrite, and yeah, if you can just give us a brief overview of I guess the responsibilities and I guess yeah, kind of like your journey through implementing it.
Yeah, sure. Hi, everyone. I'm Will. I'm a backend engineer on the GitLab team. So I work with Go pretty much entirely, basically, in that role. Prior to joining GitLab, I was on the support team, and there I'd written a few um, tools for the support team to use in Rust because we were dealing with, large volumes of client logs in particular, and we needed to efficiently parse through them. And it was taking like 10 or 20 minutes to parse a gigabyte of logs in Ruby, and we could do it in 20, 100 milliseconds in Rust. So that's how I ended up spending more time with Rust and just building uh, tools that we could give clients very easily and run ourselves, and then do high performance work. Anyway, so well, I guess before I get started on how the implementation of the client library. Any opening questions or like what is it or anything like that?
Uh, I guess yeah. I'm curious. Can you like give I guess like some more insight into how it's used to yeah, I guess like what it collects and how
Hmm.
it works.
Yeah. So basically, each Puma or Sidekick process that we have on a web service node will write its metrics out to a .db file, which is stored in a memory map directory. So I think it's var run something or other on the omnibus instances. Um, and so, but you might have 15 Puma processes or whatever running. And so when a Prometheus server reaches out to each of these nodes or web service pods and says, "Hey, give me your metrics." We need to aggregate the metrics from each of these files into a single response. And so that's basically what this library does. This was originally forked from a Ruby version, and that was implemented in C. And so what it does essentially is it parses each file, creates like a giant hash map, and sorts it, and then converts that into the text format that we respond for Prometheus queries. So basically, there are two parts to it. Let me share my screen. Start going through it. So there are basically two paths. So there's kind of the read path. Is that you see my terminal? I'm not sure I shared the right one.
Yes.
Okay, cool. So there's a read path, and so that is the computationally expensive path, which is a client is or the Prometheus server is reaching out and saying, "Hey, give me your metrics," and so that's where we're aggregating all these DB files, and we're doing that for each request, and those are run every 10 seconds roughly, and sometimes there are multiple servers hitting, so you might have one effectively every 5 seconds. So it's quite expensive in terms of CPU time, and it's purely bound in CPU. So the faster we can tear through the data, the faster we can get the response out. There's
So there's
no
no IO, just not IO bound at all.
not really no, yeah, because the files are already memory mapped. So basically, they're probably already paged in the common case. So we're not really waiting on disk. We're not really waiting on network except at the very end, and that's there's no crosstalk, right? So you get the request, you process it, you send it, you're done. There's no like waiting for a response to come back after that. So there's the read path, and that's the expensive one, and there's a write path, which is um, a one of the Puma processes wants to update its database, so then it'll call into this library and it will update the appropriate file, which is mem mapped, and basically it's just an append only format for the most part. Why don't we start with the read implementation? That's a little more interesting, I think. Okay. So that's this. So there are a number of Ruby methods. So this is using a language called, or not language, a library called Magnus to interface with Ruby. There have been like 4 different Ruby binding projects over the years, and they've gotten better over time. Originally, they were using standard like macro rules macros, where you have like, so you do like method exclamation point, and then you like write your method in there, and that's very hard to type check and validate that it works right. This is using oh, I just forgot the word. Anyway, the other kind of macro, the fancier one that like Sereda uses and so forth. I think starts with the P, but I'm blanking on it right now. Anyway, so it's looks like regular Rust types, but under the hood, it's being converted into Ruby, and it's fairly efficient. Anytime you're calling Ruby code, you are risking getting blocked by the GVL, so you need to be very cognizant of that. And there are limitations, like you can't take a reference to a Ruby object and then like try to store that on a heap. That can lead to memory
Did you
corruption.
say GDL? They mean the garbage collection?
The global VM lock. So yeah, that can be held by the garbage collector. I think there are other things as well. So like running native code, to my understanding, and I could be wrong, is that will also lock the GVL. So that's something we ran into with libgit 2, where you could be doing a really expensive Git calculation in libgit 2, which is all C code under the hood, right? So that would be running, if you're calculating some expensive diff or something like that, for a second or two, and then everything else on that process would be blocked from proceeding by the GVL. Like with Sidekick in particular, that was expensive because we could have 15 or 20 threads all sharing the same process. And with Puma these days, it could be an issue, though we basically got rid of libgit 2 at this point. Back when there was more of a problem, we were using Unicorn, so that was a single process. And that wasn't much of an issue there. Anyway, so basically we implement different methods here. So this, for example, is one. So this is the equivalent of the new. So Ruby passes in the class that it wants to provide, and then a slice of values, which is like the underlying Ruby object, which could be anything, and then we have to scan the arguments here to capture what we want, and then so we only have one argument, which is the path of the file that we want to lock, and then we create a Rust wrapper there. This is a little bit more complicated than you might expect because we need to support inheritance, because the Ruby code will inherit from the class that we export from here, which is this fastMMF file rs class. And anyway, I won't get into that. That gets complicated. Anyway, so toMetrics is the method that we use when a scrape request comes in. Well, let me pause here and ask: is all this making sense so far? Am I
I had one question. Like, could you have just avoided that by using functional patterns in Ruby, like injecting this thing and instead of trying to use subclassing?
Potentially. I was very deliberately trying to keep everything the same from the Ruby side. So this is an exact, or as exact as it can be, port of the C library to Rust.
Okay,
so
that makes sense.
So like if we look in the error classes that we have, so like we have this legacy error, which is any error message that the C implementation returned. We just try to return the exact same error message, even if it is not particularly useful sometimes, just so that if there were any clients that were relying on this, we can, they get the same response that they were always getting when stuff broke. And so here we are using this error to kind of create an enum of all the various objects or an enum of all the various errors that we could have. Where do we actually implement that here? Yeah. Anyway, sorry. There's a lot to go over, and I'm probably confused everywhere at once. Okay. So basically, this map is the hash map I mentioned of like every entry that we have. So for a given metric, let's say we have 4 Puma processes that are all writing metrics. We could have 4 of those in, like 4 separate values for that, in one for each file, right? And so then we need to aggregate those into a single value. So we call it aggregate files here. And this is not typically how Rust handles things. So like pre-allocating is, a good thing to do for performance, but like try reserve is a little bit unusual. But we're trying to capture allocation failures up front, if there are any, just to avoid panics. So like a panic is not a safety issue, but it is not a great user experience. So if we just allocated the normal way here, just with a reserve, then if that failed, which typically it's not going to on Linux, although we have run into memory issues specifically with the memory mapped region that we're using, so it's not impossible. Anyway, so if we were doing that, then I'd panic and we'd log an error that, hey, we panicked trying to do this, but this way we can capture it and say, hey, we tried to allocate this much memory, we couldn't, and it doesn't crash the process either, which is the big benefit.
Better to fail fast.
Yeah, exactly. Yeah, so this is a little bit unusual. Like typically you don't see try reserve in normal Rust code, I would say, but it obviously depends on the situation. And so then here we're allocating 16K. And then so basically we're getting a list of files that we need to aggregate. Ruby will walk the disk and find that, and then or the memory mapped area, and send that to us. So we don't walk that here. We could have done that in Rust, and that was there's kind of a competing implementation that Sylvester did that. But this maintains the original API, so no Ruby changes are needed, and it doesn't really make a difference in performance. So then we just take the array of arguments, and then we open each file, then we read each file in the memory, and then we process the buffer. And so maybe that'll be interesting to look at.
So that's where all of the performance gains are, this process buffer.
Well,
compared to the Ruby implementation.
Well, it's the C implementation. Yeah, so I guess there are kind of probably 2 things going on. One is that the C implementation used RB-strcat to build up its response string, and that could get quite expensive because each time it was calling into Ruby to do that, and we don't do that. We used a Rust string internally, and then at the end, when we have finished building it, we then convert it into a Ruby object and pass that back to the Ruby process to continue with. So I think that's probably the biggest gain. We also do some trickery with we copy a little bit less data, which is easy to do with Rust and not as easy to do with C safely. Let me show you that actually. Where is that? It's in the map, isn't it? Yeah. Okay. Okay. Yeah. So here we go. So basically, as we read each entry off of the file, we've already read the entire file in memory. What the C implementation did was it would then copy the JSON blob, which is embedded in each entry, and then, if needed, copy that into its hash map. But what we do, and what we can statically assume is safe, is we borrow the original section of the file that we read in and say, hey, is this present in the map? If it's not present, then we copy it into the map. If it is present, then we don't need to copy it. We allow that copy. And in the common case, there's a good chance it's already there. So we save a fair amount of copying. And then we can just update the value, but not the JSON string, because the JSON string itself is essentially the key. There's a little bit more. Actually, here's the key right here. You can see JSON, which is a borrowed string, and then the PID, which is also a string, but it's a pretty short. Maybe show you where we actually enter that. That's
Sorry,
where we actually read this. Go ahead.
Just a question about so I noticed the lifetimes on Yeah, I guess on the borrow data. In this case, if you were to remove that, then I guess you explicitly need to list these, right? Because they need to, the compiler needs to enforce that they both live the same amount of time.
Yeah, so this wouldn't work. So we need the explicit lifetimes because we are intentionally taking data that we don't own here, right? So we're taking this. This is from like the buffer that we've copied out of the file into our own internal buffer. So we're just borrowing from that buffer as opposed to copying the JSON string like here into its own separate string. So by doing this, we avoid the copy, but it does add the complexity to the function signature. So basically, unless you can prove that there's some kind of performance benefit, this is not worth it. In our case, it was. Profiling is good, but yeah. So usually it's not worth the hassle. It just depends how many times you're doing it. And this was kind of in the hot path, so it was worth doing. But in general, start with a copy and then see if it's expensive.
Awesome, thank you.
Okay, where do we actually use this? To show you, we do some weird stuff with the map too. Yeah, okay, here we go. All right, anchor files, sort mortar stir. Yeah, okay, here we are. Yeah, so one other thing we're doing here, so the standard hash map API that's available on stable kind of requires an owned key. But we didn't want to, so and the ultimate key that we have here is the owned key, but we want to convert that after checking if it's present. So we use hash brown, which is actually what the standard library uses under the hood for its hash map. So that's based on like Google's C++ hash map, but converted to Rust. And it provides the raw entry API here. And so that lets us like manually hash it. So we calculate the hash up here, and then we check the data to validate it's the same. And then from there, we say, okay, do we have a vacant entry? And if we do have a vacant entry, then we convert it into owned data and then insert that. If it's already occupied, we don't need to convert it into owned data. We can just keep it as the borrowed data and then take the value that's associated with the borrowed key and then merge it, which depending on the type of metric might be adding, might be overwriting, might be, well, those are I think the two most common ones. So this is a little unusual. This is not typically something that you see with a hash map. Usually the entry API is good enough, and you might have some extra copies in there. But this was again in the hot path, so it was worth it to use this kind of exotic API that's only available it's available nightly. But if you want to use stable, which we are, then you can use the hash map crate, or hash brown crate, which, like I said, is actually what is used by a standard library.
What profile do you use? Is there one that comes with Rust, or I don't know anything about it?
Well, so yeah, so it's the release profile. The way it works in Magnus is a little weird. Let's see. Let me look here. So we actually had to set a bunch of different linker flags to get it to work properly. And it's also like system dependent. So like we need to have this extra dynamic lookup flag, which is only available on Mac OS. So basically what we're saying is because we're creating this as a C library that Ruby can consume, we need to like prevent Rust from cutting out all the code it can't prove is being used. So typically when you're creating a library, this is not necessary, but because we're doing this as a Ruby thing, it gets complicated. We can look at, I think there's something else in here. Yeah. So cdylib or cdynamic library is what is consumed by Ruby. And then if we had any integration tests, which I never actually added any, but I was experimenting with it and found that I couldn't get those to work without also creating as a lib crate type. But yeah, so when it actually builds it, it'll be a release profile. And it'll be really obvious in terms of performance if for whatever reason it was using debug. But we don't directly call cargo build. That's actually run through rake. Where is it? I think it's just a rake file here. Yeah, so we have this extension task and we build a native tab. Yeah, okay. Yeah, so I don't remember offhand which one exactly runs this, but yeah, so this will handle all the interfacing with the Rust C and Cargo to actually build the library. Okay, what are the things I can show you? I guess maybe I can show you some tests. That might be interesting. So we have the test is in on the file, which is typical in Rust, although some folks, I think on very large projects, it can actually significantly improve compile time to make a separate test file. But for a project this size, didn't really make a difference. And then so like here I added a helper method for entry data. It's only useful for tests, so we just implement it here, and that way it's available for testing, but doesn't clutter up the actual binary when compiled for consumption. And so this is, do I have any table-driven tests here? It doesn't look like I do. Yeah. Oh, right. Yeah. So there's a bunch of boilerplate you have to do to get a Ruby interpreter available in tests. It's a real pain. And actually, you can't run cargo test against a library that's using Magnus directly. We actually have to use a different tool called Cargo Next Test, which is a separate test runner that you can add just to Cargo. And the reason we have to use that is because it runs each test as its own process. And there's no safe way to inject one and only one Magnus process or init Magnus once. I mean, there probably is, but it wasn't worth the effort. So we ended up using Cargo Next Test, which lets us run each test in some process, and that's safe because, well, you can't run Magnus more than once in a process; it'll panic on you. So that was kind of a pain. Okay, maybe I should show you.
So what I was asking is like when you were doing the profiling to like determine that the borrow actually helped, like what tools do you use for that, and how do you analyze the data?
Linux perf, pretty much.
Okay, so system level ones, not like Rust specific ones.
Yeah, there are some pretty good Rust profiles out there. I think, was it ByteHound? Was that it? Yeah, ByteHound is an interesting memory profiler. Put that in the Zoom chat, I guess. Yeah, I've used that in Anger in the past, and it's pretty powerful and nice. You can kind of create like custom queries against it as your profiling to understand where memory is being used. So that's a memory profiler as opposed to a C profiler, and there are flame graph tools you can build into a Rust binary. I think it's like flame graph is the name of the crate, something like that. And those are pretty easy to use. In my case, I was trying to compare the C versus the Rust implementation, so it was more convenient just to run both in like a little script and then just see where each was spending its time.
And then to figure out like the borrower versus not, like you ran two different versions of the Rust and just compared them next to each other.
Yeah, exactly. And you can really, it's usually pretty easy to see like, hey, I'm allocating a lot in this function. So, it's just like malloc. So you can, and free is actually surprisingly expensive because when we're creating the string, we end up freeing like each object as we go through it. So we actually spend like 20% of the time creating the response is just freeing each object as we process it. But I don't think there's really a way around that. At least not one that is easy to do. Okay, why don't we talk about the write path a little bit because it has some interesting Ruby shenanigans. So kind of the challenge that the C implementation and also the Rust implementation has is that we've got this memory mapped string that we're returning to Ruby, but Ruby, as we create more objects or more entries in the memory mapped file, we may need to increase its size, which involves dropping the existing memory map and creating a new one at the new size. So that means any Ruby object that has a pointer to the old memory mapped address will segfault if it tries to read that string. And so the solution that was arrived at originally in C, and we just copied it over to here, is we create this weak map. And so every string that we create, we track in the weak map, so that way we don't block the GC from reaping those strings as they get used up, but we can still find all of them. Where do we actually update that? Because it's kind of interesting. Yeah, okay. No, that's the wrong one. Here we go, update weak flag. Okay. So basically, we get the new length from the inner object. So the inner object in this case is the actual memory, the new memory map that we've gotten. So now we do iterate over each value that we have in there. And so we're actually calling the Ruby each value method against the weak object Ruby object, and then so this is kind of like Rust mixed with Ruby in this block here. And so then we create a string from it, and then here we get into unsafe, and this is not safe at all. So we convert it into like the internal representation that Magnus is using, and then we have to calculate for shared strings. So Ruby has a performance enhancement, or where it will, if you have two strings, like you have a parent string and then you want to take a substring of it, if that substring starts from some arbitrary offset and runs to the end of the original string, then it'll create a shared string. So it doesn't need to allocate a new buffer. It'll just say, hey, take this other buffer with this offset. So we need to then update any shared strings that are created as a result as well. So we have to calculate the pointer offset and then update it for each shared string that we have as well. So that's what this whole section is doing. Yeah, so it took a while to get right. At the test, do we have the test down here? I think we do. Yeah, here we are. Okay. That might be interesting to talk about here. Yeah, so basically we create strings, resize, then validate that we can still print them at the end to make sure that this works. Okay, so that took a while to get right, just because the C implementation hadn't handled shared strings, and for whatever reason in Ruby 3.1 in particular, we were segfaulting a lot on that one. Like the other Rubies, 2.7, 3.2, 3.0, it basically never happened, but in CI all the time, 3.1, this scenario would happen. I don't know if they got more.
The C implementation didn't have a problem.
Well, it did. It just had it less often, and I don't think we were testing 3.1.
It was like really the version before they started doing that optimization.
Yeah, exactly. Yeah. So let me talk a little bit. Go ahead.
Means that like you want to do matrix testing of this on CI, especially for versions.
Exactly. That is what Stan ended up implementing. Later on, like as we were working through this rewrite, he improved the CI a lot. So we do that now, and that's how we ran into this scenario, actually. But it was kind of another hidden foot gun that we weren't aware of when I started the rewrite. So let's talk a little bit about kind of the way this is set up. So we have this memmap file struct, which is kind of like the object that is exposed to Ruby. And then that is a wrapper, a tuple struct around a read-write lock. Ruby also has a lock around this. We were not 100% confident that it was being implemented properly. So this was added to prevent any race conditions. And the reason we have to do this in the first place is that any method that Magnus exposes to Ruby has to be as a borrowed reference, or an immutable reference, right? And so we need to use this read-write lock to kind of like trick it into allowing us to mutate it by giving ourselves exclusive access in a thread-safe way. So the immutable method here is actually a lie. And then we have an option of an M, and then the inner mmap is the object that actually holds the actual mmap itself. So if you look at that, so that will have a file, and then the path of the file, and then here is the actual memory map, and then the length of the memory map, which is usually but not always the same length as the length of the memory map itself. So this is like the length of it that we actually have written data to versus the length that's available. And that took me a while to look at the C notation to understand what real meant. Okay, so basically what this lets us do is by having an option of this inner map when we resize. Where do we do it? So there's mmap is one method we expose. Where do we actually resize it? Yeah, here we go. Expand to fit. Okay. So RB self here is the mmap file or the outer object. And then so here we that's our pointer. Okay, this is for update the capacity. Oh, actually I should mention this. So you can see all these like cast check. So typically you can just do a standard Rust cast. I was really worried about, because we're taking arbitrary values from Ruby, I was worried that we'd have overflows or something like that. So we have this cast, which is a wrapper around the try-froms, essentially, or in checked adds and check multiplies. So that way, should we overflow or be unable to convert the value because like the conversion from a CENT to a U size is not valid, for example, then we catch that at runtime. It's not really a safety improvement per se. Like Rust, if you try to do this and then like we passed an invalid index into the file, it would still panic because it would be out of bounds. But this way, we return a good error to the user saying, "Hey, you tried to access at this index, doing this operation." So that's the reasoning behind that. Like usually you don't do that, particularly in like any kind of like application code as opposed to library. I don't know, there's much of a benefit there. But this is really just to prevent us panicking. Okay, so anyway, so when we're resizing, so we have to remap the file. So we have to take the original inner map, take ownership of that here. So then we are, yeah, we're just trying to get that. Okay. So we take that, we've like removed it out from inside ourselves at this point. And then we take the file from that and expand it. And then we create a new inner mmap and then insert that into ourselves. So that way, so you can see like, even though we're doing all this stuff to ourselves, we're still saying this is a immutable borrow to self, but it's not really. We're just using the read-write lock to allow ourselves to do that because we're guaranteeing exclusive access to the object using that lock. Originally, I actually had refcell, which does the same thing as a kind of way to like hide the mutability. But because we were worried about synchronization and multiple Ruby threads, we switched over to RW lock. But either one, depending on the situation, would be fine. Yeah, so like, most of the Rust documentation talks about mutable versus immutable borrows, but really a better way of looking at it is exclusive versus shared borrows. So by using the read-write lock, we were getting an exclusive borrow, and so we can mutate even though we still we have the shared borrow syntax there. Does that make sense?
Yeah. I have a question as far as the lock itself. Like, is there any chance that it could deadlock in this scenario?
No, because basically we have it so that anytime we take the lock, we panic. So like if it would deadlock, if we would wait, then because we don't panic, we return an error saying this mmap error, concurrent access error. So because we're expecting Ruby to always be synchronizing on its end, we're not really concerned about actually handling concurrency on our end. This is more like a safety check. And then we'll just return this error saying, hey, you had multiple threads trying to mess with it. That's never happened.
Okay.
But that's a good question. Yeah. We're not really worried about it in this case because we don't actually expect more than one thread to touch it.
Okay. And like kind of related to this, as far like in Go you have like the defer statement, and like so the very common pattern is like you would defer, like if you have a lock you would defer the unlock, so in case you don't forget for this you don't forget that operation. Is there anything like similar, like let's say you wanted to guarantee that in Rust? Is there something similar, or do you
Yeah, so
have
there's
to
no
do that
defer
yourself?
statement. But typically what you do is basically you'd have a scope statement. So Rust uses what C++ calls RAII, where the lifetime of an object is based on scope, right? So you would take your lock of mutex or whatever, and then while that lock was in scope, it would be locked. And as soon as the lock drops from scope, it also drops the lock as well, right? So that way you don't have to worry about forgetting to defer. You lock, you use it, you drop, you leave it alone. It's out of exit scope. You're unlocked. So that's the pattern that Rust uses, and you can see that. Where is it? We don't have the lock per se, but when we take the inner and then we drop it. We're taking the inner and then we're mapping it. And so we're not explicitly saying, hey, drop this, but because we've taken the inner and then we just left it alone, it's no longer in. Let me pull up the Rust docs. I think the mutex docs are pretty good on this, actually. One sec.
You're not sharing this if you're wanting
Yeah,
to.
no, this is on a separate screen. Sorry, I'm just trying to find a good example. This is all. Yeah, so like here, so here we have the mutex, and we take the lock, and then this unwrap is just saying, assuming we didn't deadlock. And so then as long as that's in scope, we hold the lock on the mutex, and then as we exit the scope in here, then the mutex guard gets dropped. So the mutex releases the lock as we exit scope.
Oh, this is cool. So in a way, it's even safer than like something like Go, because you have
Mhm.
to be I guess explicit about using defer. Here is already automatically done for you and ensures it's always freed.
Yeah, exactly. Yeah, so this is something that's really common in the Rust standard library. So like for example, with files, it is the same thing. Kind of the downside is when you drop a file, like it closes the file as you drop, but it also prevents you from actually checking like were there any errors when I closed it, which you may care about. Um, so that's kind of the gotcha with this is yeah, okay, here we are. Errors checked and close the error, ignore but implementation to drop. Yeah. So that's kind of the downside is like you if there is something that could fail as you're releasing whatever resource it is, there's no good way of checking that. So you really have to find some other sideband way of validating if there's an error before you drop it.
Awesome. Thank you.
Sure. Any other questions? I know I've talked a lot.
What did you say that? I know you said at the beginning. What was the performance improvement you got out of this
It's about
improvement?
4 times higher than the C implementation was.
What does that translate into, like actual request times for the average load?
Let me. Which is that it? No, this is it. Okay. Let me see if I can find the issue. Pull this over the side for a sec. Stan had some documentation on it. Let me find that. Okay, here we go. Yeah, so you can see here the green line was the region we'd already enabled it in, and then the blue and the red ones are maybe a little bigger. And the other two are the C implementation. So basically, as the size of the metrics data on disk increased, the relative improvement in Rust also increased. Just
The
because
spikes are proportional too.
yeah, so these spikes are actually when a new pod is starting up. So we run GC, Ruby GC for every request. And typically there's almost no garbage, except when it's first starting up, and then it's created a bunch of objects. So there's a long GC pause right at the start. And so that's why all three of them have these large spikes sometimes. It's not actually anything to do with the processing of the data itself. It's just the Ruby VM is locked when we wait for the GC to run. And then after that, it smooths down. And so these are the normal jitter that you see in requests.
So the spikes are a lot smaller in the rewrite because you're not dealing with the data in Ruby and getting garbage collected as much.
Well, so yeah, so it's not so much that we're sending less data to Ruby. Like the ultimate size of the response should be identical to what the C implementation is sending. It's just that the way we handle the data in Rust is a little bit more efficient. I think the Rust sorting algorithm is probably faster than quicksort, which is available in the C standard library. That's what he was using. And I'm quite sure that the Rust hash map, hash brown, is more efficient than the hash map that was being used in the C implementation. It was just kind of a generic hash map that someone had thrown up because, C doesn't really operate a hash map, right? And it just doesn't receive the same kind of attention to performance that the Rust one has. So it's not, other than like the borrowing trick that I mentioned, where we don't insert into the hash map or allocate for insertion into the hash map unless we absolutely have to, like the RB stircat that we're avoiding. Those are kind of like the two things that we're doing in our own code to improve performance. The rest of it is just, like Rust's libraries out there, often more performant than what's available for random tasks than what's available for C. It depends. But anyway, so you can see it gets up to around 8 seconds, and this is across like 20 pods or something. So like the actual response time it changes from like 150 milliseconds to 30 milliseconds or 40 milliseconds, something like that, per pod. But and this is aggregated across all pods in a region. So it goes from 9 to 3 or 2. So that was the performance change we saw. So that was pretty good. Like we got the safety of Rust, which was kind of like the original purpose of this, and then it turned out that we could also make it faster as well. Just because like Stan was the only person who had really dealt with the C implementation in any depth, and it wasn't really being maintained, and it was just kind of decaying over time. All right.
I'm curious. I'm curious about your use of self.0. Like I haven't seen that idiom. Where does that? Like, yeah.
So because we're using a tuple struct here, so self.0 would be, so like if we had this memory map file, 0 would be the read write lock. So like if you had a tuple, like for example, then you could do, or actually, no, that's not what we should do. And you could do zzz.0. So that's the typical like tuple syntax. But when you're using a tuple struct, so a struct with the the curly parentheses or the curved parentheses instead of curly braces and named fields, then I'm sorry, that's down here. Then you can use the same syntax for 0 being the first field, 1 being the second field, and so on. So yeah, it's a little less common with structs. When you're using something that's just like a straight wrapper of some other underlying item, then it's pretty common to use a tuple struct. But if like for example, the inner item, here we're using a standard struct with with name fields, because the outer one is really just intended as a wrapper that handles all the Ruby processing of the inner item. We used a tuple struct here. So we could have done something like this, and then it'll just be, self.lock, but it doesn't really add much because there's really only one item in this struct. There you go.
That makes sense. Yeah, I guess I wasn't up to like the tuple struct construct. That idiom I haven't seen it yet. Like, so yeah, that makes sense.
Yeah. So wrapper types in Rust are a pretty common way of like extending someone else's type that you want to use for yourself. I think if you just Google for that, you'll see a ton of literature out there. But yeah, so that's what we're doing here. Any more questions?
I had some. So like
Sure.
I guess like as far as the process for like doing something like this at GitLab, like, what would you say your experience was? Was it like hard to find a reviewer? Would you like to see some like guidelines or like maybe something like I don't know, like a danger job or stuff like that included for specifically with Rust in mind?
Yeah, so yeah, reviewer is certainly a challenge. Stan was the main reviewer, and then Mocon also did some reviews, but really and I know there's at least Anthony on the security team who has since left. I know had worked with Rust in the past, but I don't know if there are that many people who have worked with it in general. Like certainly not as like a part of their day job at GitLab, right? So yeah, finding reviewers is definitely a challenge. In terms of, I'm not going to find that. Where am I? Danger jobs, we do run Clippy against it. So we just do cargo Clippy and then we're passing in the path. So like if it was a straight Rust project, you could just run cargo Clippy. So that, is kind of like the standard linter for Rust. It's quite good. It will capture a lot of stuff and we'll give you like actionable examples and explain how to do everything. So we shouldn't have any clippy lint on this right now. I guess we can check. Oh, that's right. I'm going to see one. So if I go to the right directory. Yeah, so that's clean. But if there was one, then it would be caught in CI. So yeah, I do recommend running Clippy against anything you build. And there's also Rust format, or Rust fumped, however you want to say it, which is equivalent to Go fumped, and it's quite nice. It does have more options, I think, than Go, just because Rust syntax is much more baroque than Go's, for better and for worse. But it's also good. Yeah, good question. Any other questions?
I have one more, but if anyone else wants to ask first. Yeah, so the last question I had was like if you see Rust fitting in anywhere else, so you mentioned you did the improvement from minutes to milliseconds for the log file ingestion.
Yeah.
And then you've also worked on this project here for the Prometheus scraping. Yeah, do you see anywhere else where this would be a good fit? Like maybe any patterns we should look for?
Yeah, I mean, anything that's computationally expensive, I think, is a good fit for Rust. So like there was actually an attempt to rewrite this in Go about a year ago, and it didn't really work out. Like part of it was that releasing the memory, with any kind of regularity was much more difficult in Go because it's got the GC, it doesn't really know how long to hold on the object. All the memory usage here is extremely deterministic. And Rust is just efficient too. There's no runtime, right? So if you're doing something where you profile it and you're just spending a ton of time on the CPU and nothing else, then I think that Rust might be a good fit for that. So CPU and memory intensive as well. Because this was consuming, it could be 50 to 70 megabytes of metrics that it's pulling in per request. And then if it holds on to that for a while and you're taking a request every 5 seconds, it can add up to a lot of memory pretty fast. But because all the memory usage here is scoped, so like just like I was talking about with like, we drop the mutex lock at the end of scope, that also happens with any memory. So like we allocate a new string, the string drops from scope, we drop the string from memory as well, like at compile time. We know that's going to happen. So there's no wishy-washy, how many strings do I have left at this point? You know exactly when they're gone. And that can be extremely powerful. So I think that answers your question.
Yeah, thank you.
So if you hadn't have had to preserve, the existing contracts, you could have rewritten the Ruby code like how you want. Like in addition to maybe not using inheritance and just injecting something functionally. What else could you have done to not have to jump through as many hoops to interface with Ruby?
Yeah, so that was kind of like the main challenge with interfacing with the old code. Excuse me. Other than the substring issue, which I mentioned, which is just kind of inherent in that Ruby object lifetimes are totally indeterminate, and maybe we have this like hard deadline of when they can be used on the C or Rust side, and it just doesn't translate over. Yeah, so in general, we could just do a straight copy of the methods as the method signature from what we had in C over to Rust, and that if we look at the C, I think it was here. Was it here? Maybe it was. Let's see. No, I think it was this one. Yeah, okay. So like here we're doing this. So the way the C did it was like it defined its own allocation. So this is essentially what we end up doing in Rust. It's just like when I started using Magnus, there was an issue where it didn't support that. So like the default way you create an object of Magnus, it doesn't support, or a class of Magnus doesn't support inheritance. So like I said, that required some hoops with like creating this initialize method, which is basically doing the same thing that we're doing here in C, just a little more verbose and with actual comments. But yeah, so I don't know that I would particularly change anything from the Ruby side. I'm not much of a Ruby developer, so I would certainly defer to pretty much anyone else on this call for thoughts on how to change the Ruby.
On the remote development side, like I'm in the process, I talked a couple of sessions ago about rewriting it to use the result class that is almost exactly based on the result class or the result type in Rust, and the code is so much better. And like everything is a class method. There's no inheritance, there's no state, there's no instance variables, and writing things functionally like that, which is still pretty close to idiomatic Ruby. Like you can do higher order function, you can pass a method, you can pass a lambda, but it just, everyone who's looked at it says, oh my gosh, this code is so much easier to understand and reason about than a nest of hierarchy and mixins and modules.
Yeah, absolutely. Yeah, so like certainly the result type is,
and like looking at that, you think about the problem differently, like to be inspired by how Rust approaches the problem.
Yeah, for me, like result and enum are the two things I love most about Rust. It's just, like every time I want to express some kind of enum on Go, it's just like, oh God. And then it's just so much more expressive in Rust. And you just know a compile time that you've covered all the problems instead of like, well, I hope I didn't increment that iota wrong. It's just a world difference.
All right, this was great. Thanks for that.
Yeah, thanks for inviting me. I really appreciate it.
Thank you all. See you next week or 2 weeks from now. Bye.